Good afternoon, dear students. I am Akshata Patil, lecturer, Department of Mathematics, VDIT Halyan. Today, we are going to discuss variational problem and what do you mean by Euler's equation. Okay, so in today's class, let me recall the definition of functional, variational and extremal of a function. Okay, so here I have once again recall the definitions here. So what do you mean by functional? So in yesterday I have already explained the definition of functional. So functional means it is nothing but the integral value of a function with the given boundary condition. Okay, so that is nothing but if I consider a function f that is f which is equals to f of x comma y dash where x is lies between x1 to x2, then the integral then the integral capital I, which is equals to the integration over x1 to x2 f of x comma y dash into dx is called a functional associated with the function f of x comma y dash. Okay, now this is nothing but the definition of functional. So yesterday I have explained already this one. Okay, so once again I will recall the definition of functional. Functional is nothing but what? Integral value of the function with given boundary condition. So this is boundary condition they have given. So here I have written consider a function that is f equals to the function of x comma y dash where x is lies between x1 and x2, then the integral capital I, which is equals to the integration over x1 to x2 f of x comma y dash into dx is called a functional associated with the function f of x comma y dash. Okay, in other words we can say that functional is a mapping from functions to real numbers. Okay, now this is a definition of functional. So in yesterday I have discussed one more definition, that is extremal of a function. Is it right? Extremal of a function. I have explained it already. So once again, I will recall the definition of extremal. Now, what do you mean by extremal? Extremal in the sense what? Maximization or minimization problems dealing with this. Okay. Now, when do we say that the function is extremal? If I consider a function, okay, if I consider a function capital I, okay, usually the functional is denoted by capital I, and we know capital I, which is equals to integration over x1 to x2 f of x comma y dash into dx at this epsilon, which is equals to 0, epsilon equals to 0. Let's see what will happen here at epsilon equals to 0. Okay, now suppose at epsilon equals to 0, then capital Y coincides with small y. Okay, and similarly here at epsilon equals to 0, then capital Y dash coincides with small y dash. Okay, therefore that is we can say the I of epsilon becomes capital I because epsilon is 0. Because epsilon is 0, that means di divided by d epsilon, which is equals to 0. That means di by d epsilon, that which is equals to 0, it means there is no change in the functional with respect to epsilon. Okay. Now this is a definition of extremal of a function. Now what do you mean by extremal of a function? Extremal of a function means here if I consider, we can say here either maximization or minimization. Okay. Now if I consider a function I, so we know what do you mean by I? I is nothing but what? Integration over x1 to x2 f of x comma y dash into dx at epsilon equals to 0. Now what happens here at epsilon equals to 0 means at epsilon equals to 0, then capital Y coincide with small y. Similarly, the capital Y dash coincide with small y dash. That is, I of epsilon becomes I because epsilon is 0 here. That means di divided by d epsilon, which is equals to 0. It means there is no change in the functional with respect to epsilon. Okay. Now this is a definition of extremal of a function, which we have already explained in yesterday class. Okay. Now in today class, let us see. Let me explain why we required Euler's equation or why variational problems arises. Okay, as we know, we are aware of the fact that what exactly the application calculus of variation being used in case of dynamics of a rigid body, variational problem arising due to the maximization or minimization problems and all other concepts which has physical phenomenon which deals with the maximization and minimization problems. Okay, now let us see what is the variational problem and Euler's equation. Now let us see the definition here, variational problem. Now, what is the definition of variational problem means? If we have to find extremal of a curve, okay, here if we have to find extremal of a curve, that is capital Y equals to y of x for the functional in the sense what, which here we can denote it like this capital I. Okay, function means we have to use this notation here. Okay, so for the functional I which passes through the two points, okay, which passes through the 2 points, that is x1 comma y1 and one more is x2 comma y2. These points must satisfy the two conditions. Okay, must satisfy the two conditions. So here what is the definition of variational problem? If we have to find extremal of a curve, we already know what is the definition of extremal of a function. Okay, so here if we have to find extremal of a curve, that is y equals to y of x for the functional capital I which passes through the 2 points, that is x1 comma y1 and x2 comma y2. These points must satisfy the two conditions. So first condition is what? Delta I which is equals to 0. That means delta I which is equals to delta into integration over x1 to x2 f of x comma y dash into dx. Okay, and the second condition is y of x1 which is equals to y1 and y of x2 which is equals to y2. Okay, now this is a definition of variational problem. Here in these two conditions, let's see the condition number 1 is called variational equation and the second condition is called boundary equation. Okay, now here we can, if you want, you can write here in these conditions, condition number 1, condition number 1 is called variational equation, and second condition is called boundary equation. Okay, so I hope you understand what do you mean by variational problem. Variational problem means if we have to find the extremal of a curve y equals to y of x for the functional capital I which passes through the 2 points, that is x1 comma y1 and x2 comma y2. Now these 2 points must satisfy the 2 conditions. So first condition is delta I equals to 0. So delta I equals to 0 means we already know the definition of functional. Okay, so delta I equals to 0, it means here we will get delta I which is equals to delta into integration over x1 to x2 f of x comma y dash into dx. Okay, now second condition is what? Y of x1 equals to y1 and y of x2 equals to y2. In these two conditions, condition number 1 is called variational equation and the condition number 2 is called boundary equation. Now this is a definition of variational problem. Okay, I hope you understand the definition of variational problem. Now let us move very important theorem, that is Euler's equation. Okay, now the statement says that, now let us see the statement of Euler's equation. The statement says that a necessary condition for the integral capital I which is equals to integral over x1 to x2 f of x comma y dash into dx, where y of x1 which is equals to y1 and y of x2 which is equals to y2 to be extremum. Is dou f by dou y minus d by dx of dou f by dou y dash which is equals to 0. Okay, now this is a statement of Euler's equation. Now Euler's equation is one of the important theorem, okay, in this calculus of variation. So here statement they have given a necessary condition for the integral capital I which is equals to the integral over x1 to x2 f of x comma y dash into dx, where y of x1 which is equals to y1 and y of x2 which is equals to y2 to be extremum. Extremum in the sense what? Either maximization or minimization. Okay, so to be extremum is dou f by dou y minus d by dx of dou f by dou y dash which is equals to 0. Now this is a statement of Euler's equation. That means we need to prove that the functional I. Okay, now let us consider the proof of the Euler's equation. Okay, now let us see the proof here. Now let us consider the proof of the Euler's equation. First of all, it is a variational problem, no doubt. As we know the definition of variational problem, here we can say delta I which is equals to 0. Okay, the variational of the function must be equals to 0. Okay, so let us consider the variational equation here. Okay, so here we can write, let us consider the variational equation delta I. Okay, so delta I equals to what? That is delta I equals to what? We already defined this one. Delta I equals to integral over x1 to x2. Okay, dou f divided by dou y into delta y plus dou f divided by dou y into delta y dash into dx. Okay, so now this is equation. What it is there, which is nothing but first variational, what we called previously we have to obtain. Okay, so this is nothing but first variational. Okay, so according to the definition of variational problem, so here we can write according to the definition of variational problem, this delta I which is equals to 0, this delta I which is equals to 0. Now we know that delta I which is equals to 0 by variational equation, that means this above integral, what it is there, that is equals to 0. Is it right? Because here in by the definition this is nothing but the first variational function. Okay, so this is nothing but the first variational equation. Here by the definition of variational problem, by using the definition of variational problem, this delta I becomes what? 0. Okay, so this delta I becomes 0 means here the above integral, what it is there, this integral dou f by dou y into delta y plus dou f by dou y into delta y dash. Okay, so this integral which is equals to 0. Okay, so here we can write that is that means integration over x1 to x2 dou f by dou y into delta y plus dou f by dou y dash into delta y dash, sorry, dou f by dou y into delta y plus dou f by dou y into delta y dash into dx, which is equals to 0. Okay, because this integral which is equals to 0 by the definition of variational problem. Okay, in this above integral, okay, in this above integral there are two terms. Okay, now first term is what? First term is, that is nothing but dou f by dou y into delta y. Okay, and second term is dou f by dou y into delta y dash, dou f by dou y into delta y dash. Now here I have draw a figure. Okay, so here I will draw a figure, that is a plane, xy plane. Okay, so here I have considered the two lines, parallel lines. Okay, so I have mentioned our one curve pointed to P as well as the pointed to Q. So P means I have given x1 y1 and Q means x2 y2. Okay, now in this inside this curve, okay, so in the inside this curve, here there are 2 points P and Q, and the gap between 2 points, we says that this is nothing but this gap between these 2 points, this we says that delta y, this is variation in y, this is variation in y, because this is nothing but y axis means this is considered as y1 and this is considered as y2. Okay, now there are 2 points here, that is P and Q, and the gap between these 2 points, this gap we says that delta y, this is nothing but variation in y. Okay, now here we can write px1 is nothing but now this p of x1, this px1 is nothing but y1. Okay, and qx2 is nothing but y2. qx2 is nothing but y2. Okay, now here in second term, this delta y dash in this, see here, in second term, this delta y dash, as we mentioned in the previous class, there is one property is there. Okay, so in that property, see here, I will show you that property. This property delta I equals to dou I by dou y into delta y plus delta I divided by dou y dash into delta y dash. Okay, now here the one property, that is variational problem and differential operator, are commutative. Okay, so by using that property, here we can say a delta y dash which is equals to d by dx of delta y, because the variational operators and differential operators are commutative. Okay, are commutative means here we can write delta y dash which is equals to d by dx of delta y. What about this delta y dash stands? Delta y dash stands for variational operator. Okay, and this d by dx stands for differential operators. Okay, differential operators. So here we can, by using this graph, by using this figure, here we can say px1 is nothing but y1 and qx2 is nothing but y2, and by using the property of variational problem, okay, by using the property which I have explained in the definition of variational first variation, by using that property, here we can say the variational operators and differential operators are commutative. Okay, are commutative means delta y dash which is equals to d by dx of delta y. Here delta y dash stands for variational operator and d by dx stands for differential operator. Okay, so mean that they are interchangeable. Okay, I hope you understand this one up to this much steps. Okay, now in place of this delta y dash, in place of this delta y just replaced it by d by dx of delta y. Okay, so in this integration, in place of this delta y dash, I just replace it by this d by dx of delta y. Okay, so here we can rewrite this equation once again. So here we can write, replace delta y dash it by d by dx into delta y, then the above equation becomes, then the above equation becomes, okay, then the above equation becomes integration over x1 to x2. Okay, so first term keep as it is, dou f by dou y into delta y keep as it is, only in place of delta y dash. Okay, so dou by dou y dash keep as it is, in place of delta y dash just replace it by d by dx into delta y. So here we can write d by dx into delta y. Okay, which is equals to 0. Okay, I hope you understand this step. Here what I should do, actually this integral is there. Okay, in this integral, see, in this integral, here in place of delta y dash, what I should write here, in place of delta y dash, just I replace it by this d by dx, this d by dx into delta y. Okay, so here I have written that step, dou f by dou y into delta y keep as it is, plus dou f by dou y dash keep as it is. In place of delta y dash, here I have written d by dx into delta y into dx, which is equals to 0. Okay, now taking integrate separately. Okay, now you know how to integrate this function. So now integrate separately. So here we can take Integrate separately. This integration we have to use separately for these two terms. This is first term and this is the second term. So I will integrate separately here. So we can write integrate separately. Integrate separately. So let us take separately integration over x1 to x2. Okay, so first we can write dou f by dou y into delta y into dx. Okay, dou f by dou y into delta y into dx. Now we can write one more integration here, plus sign. Again take this integration over x1 to x2. Now let us take the second term here, dou f divided by dou y dash into d by dx of delta y. Okay, delta y put into the flower bracket into dx. Okay, into dx. So here what we should do, here we can take integrate separately to each terms. Okay, so this is integration over x1 to x2, this dou f by dou y into delta y into dx. Okay, now keep this plus sign as it is. Now again take integrate here, integrate over x1 to x2. Now second term is what, dou f by dou y dash into d by dx of delta y into dx. Okay, now here we have two integrating functions. Okay, now first function keep as it is, first integrate function keep as it is, only using integrating by parts to the second term. Okay, so here what I should do, here first integrate function. First integrate function means which function? Dou f by dou y into delta y dx. Keep as it is. So here first integrate function keep as it is. Keep as it is and using integrating by parts. You know, integrating by parts and using integrating by parts to the second function. Okay, to the second function. Now what I should do here, this first function don't use integrating by parts, keep as it is, only you have to apply the integrating by parts to the second function. Okay, so here we can write integration over x1 to x2, first function keep as it is, dou f by dou y into delta y into dx, keep as it is. Okay, now here keep plus sign as it is. Okay, now here you should apply integrating by parts to this second function. Second function means here you know the how to integrate. Applying integrating by parts means I need first term and second term. So here I will consider this is a first term and this is a second term. Okay, now here we use the integrating by parts. Okay, now first here we have to, what we should do, first term we should keep as it is it right? So first term we should keep as it is, dou f by dou y dash. Okay, now here we should integrating the second term. Integrating the second term means d by dx of delta y. You should integrate with respect to x, then you will get here delta y, and applying these limits, that is x1 to x2. Okay, now minus sign, you know Bernoulli's rule, is it right? Now minus sign, now again integration over x1 to x2. Okay, integral over x1 to x2. Now here we keep this function as it is. Okay, and you have to differentiate the first function. Differentiating the first function means dou f by dou y dash is there. Differentiating the first function, d by dx of dou f by dou y dash. Okay, dou f by dou y dash into delta y. Okay, into dx, which is equals to 0. Okay, I hope you know how to apply the Bernoulli's rule, integrating by parts. Okay, now here I have kept first function keep as it is. Now applying Bernoulli's rule, integrating by parts to the second function. Again have considered this is a first term and this is a second term. You know how to integrate this function. Okay, so here what I should do, first term keep as it is, integrating the second term. So here we will get delta y, applying the limits x1 to x2. Bernoulli's rule means here next sign is minus, again integration of x1 to x2, differentiation of first term, that is d by dx of dou f by dou y dash into delta y dx, which is equals to 0. By the end condition of variation equation, y must assumes the specified value of y1 and y2 for x equals to x1 and x equals to x2. Hence we can say, so here we can write, by the end condition, by the end condition of variation equation, we know what do you mean by variational problem. Okay, now by the end condition of variation equation, y must be assumes the specified value of y1 and y2 for x equals to x1 and x equals to x2. Okay, hence we can say here, hence delta y which is equals to 0 by using the definition of variational. Okay, hence delta y which is equals to 0 at x equals to x1 and x equals to x2. Okay, now second term in above expression is 0. Okay, means here delta y equals to 0. Delta y equals to 0 means here the second expression. What about the second expression here? That is dou f by, see here, this second expression, dou f by dou y dash my into d by dx of, sorry, this function, dou f by dou y dash, this function should be equals to 0 here. Okay, so here we can write, that is second term in above expression is 0. So here we can write x1 integration x1 to x2 dou f divided by dou f divided by dou y minus d by dx of dou f by dou y dash into delta y into dx, which is equals to 0. Okay, so just see here this expression. In this expression, second term in above expression, it means second term in above expression is 0. So here we can write only dou f by dou y. Okay, so here dou f by dou y is there, so here we can write dou f by dou y. This delta y common we will take outside here. Okay, so dou f by dou y minus here this d by dx of, here you have d by dx of dou f by dou y dash, again this delta y we can take common outside. Okay, into dx, which is equals to 0. This term, second term, dou f by dou y dash into delta y become 0. Why it becomes 0? By using the definition of variational. Okay, because here the y must assume the specified value of y1 and y2 for x equals to x1 and x equals to x2. That means delta y which is equals to 0 at x equals to x1 and x equals to 0, x equals to x2. Therefore, this is second term dou f by dou y dash into delta y become 0. So here we will get the expression integration over x1 to x2 dou f by dou y minus d by dx of dou f by dou y dash into delta y into dx, which is equals to 0. Okay, it is equals to 0. Therefore we can say, therefore delta y which is equals to 0 is the only condition imposed on delta y between x1 and x2. Okay, so this is the only condition which is imposed on delta y between x1 and x2. Okay, so delta y is an arbitrary variation of y, hence the above equation holds for arbitrary. Hence Hence, the above equation holds for arbitrary delta y for x is lies between x1 to x2. Hence we can say here dou f by dou y minus d by dx of dou f by dou y dash. Okay, dou f by dou y dash, which is equals to 0 for x is lies between x1 to x2. This equation is called Euler's equation. Okay, this equation we call it as Euler equation. I hope you understand this theorem of Euler equation, and here they have given some alternate forms of Euler equation. Okay, so here we can write alternate forms of Euler's equation. Okay, so alternate forms of Euler's equation they have given here. That is, first one is dou f by dou y minus dou square f divided by dou x dou y dash minus dou square f divided by dou y dash. Okay, dou y dash into y dash minus dou square f divided by dou y1 dash the square into y double dash, which is equals to 0. And one more form they have given, that is d by dx of f minus y dash into dou f by dou y dash, which is equals to dou f by dou x. So here they have given two alternate forms of Euler's equations. No need to derive these forms, only we have to refer these forms. Okay, so this is nothing but the Euler's equation. Okay, I hope you understand this Euler's equation. Okay, so in today class we have discussed what do you mean by variational problem. Okay, and I have discussed this Euler's equation. So in variational problem, what do you mean by variational problem is, if we have to find the extremal of a curve, that is y equals to y of x for the functional capital Y. Usually functional is denoted by capital I. So here we can write for the functional capital I which passes through the 2 points, that is x1 y1 and x2 y2. These 2 points must satisfy the two conditions. So first condition is what? Delta I, which is equals to 0. Okay, so delta I equals to 0, it means what? Delta I, which is equals to delta of integration over x1 to x2 f of x comma y dash into dx. Okay, and the second condition they have given, y of x1 equals to y1 and y of x2 equals to y2. In these two conditions, condition number 1 is called variational equation. Okay, and the condition 2 is called boundary equation. Okay, now this is nothing but the definition of variational problem. Okay, so next, here we have learned Euler's equation. This is one of the most important theorem in this calculus of variation. Okay, so here they have given statement. Statement is a necessary condition for the integral capital I. We already know the definition of functional. Okay, so here we have used the definition. Okay, so a necessary condition for the integral capital I, which is equals to integral over x1 to x2 f of x comma y dash into dx, where y of x1 which is equals to y1 and y of x2 which is equals to y2 to be extremum. Extremum means either maximization or minimization. So to be extremum is dou f by dou y minus d by dx of dou f by dou y dash, which is equals to 0, which we need to prove this one in this Euler's equation. Okay, now this is nothing but the statement of Euler's equation. Now here I have written the proof of this Euler's equation. Okay, so here we have considered the variational equation. We know this variational equation, that is nothing but delta I. Delta I, we already explained this one, variational equation. So here let us consider the variational equation delta I, which is nothing but integration over x1 to x2 dou f by dou y into delta y plus dou f by this dou y dash into delta y dash into dx. Okay, by according to the definition of variational problem, here we can say delta I, which is equals to 0. Okay, why we can say this delta I, which is equals to 0? Because here the first variational is called, here this is nothing but first variational. Okay, so by using this definition of first variational, this delta I becomes 0. Okay, so delta I becomes 0 means here the above integral become 0. Delta I becomes 0 means use this in above integral. So this is nothing but delta I. So delta I become 0 means use this one into the above integral. So here we'll get integration over x1 to x2 dou f by dou y into delta y plus dou f by dou y dash into delta y dash into dx, which is equals to what? 0. Okay, now here the first term, here two terms are there. First term is dou f by dou y into delta y, and the second term is dou f by dou y dash into delta y dash. Okay, now just see the figure here. Okay, so in this figure they have given 2 points. Okay, a curve is there, so they have given 2 points, capital P and capital 2, and the gap between these 2 points is considered as delta y. Okay, so this is nothing but variation in y. So here px1 is nothing but, okay, px1 is nothing but y1, and qx2 is nothing but, which is parallel to y-axis, means here we can say qx2 is nothing but y2. Okay, and here, okay, so now here we can use one property of variational. First variational, the property says that the variational operators and differential operators are commutative. So here we can write they both are commutative, means delta y dash, which is equals to d by dx of delta y. So here delta y dash stands for variational operators and d by dx stands for differential operators. Okay, now you have to use this delta y dash in in place of delta y dash it by d by dx into delta y in this integral function. Okay, so in this integral function here delta y dash is there, so in place of this delta y dash just replace it by d by dx of delta y. So here we will get, so here we will get, then the above equation becomes dou f by dou y into delta y, keep as it is, plus dou f by dou y dash. In place of delta y dash, here we can write d by dx of delta y into dx, which is equals to 0. Now here integrate separately. Okay, so how integrate separately? So write it down, integration, first integration over x1 to x2. First function is dou f by dou y into delta y into dx. Now this plus sign keep as it is. Again take the integration here. So integration over x1 to x2. So the second term is dou f by dou y dash into d by dx of delta y into dx. Now what we should do here, the first integrate function keep as it is. Okay, and using the integrating by parts to the second function. Okay, now here just see, here I will keep this function as it is here. Okay, now only we have to applying the Bernoulli's rule to the second function. Okay, now here this first function keep as it is plus, now this is first term and again this is the second term. Now in Bernoulli's rule means here we can write first term keep as it is, dou f by dou y dash, integrating the second term d by dx of delta y, integration with respect to x means you will get it here delta y. So applying the limits here, that is x1 to x2 minus again integration over x1 to x2. Okay, so here differentiation of first term, that is d by dx of dou f by dou y dash into delta y into dx, which is equals to which is equals to 0. Okay, now here by the end of the condition of variation equation, y must assume the specified value of y1 and y2. Okay, for x equals to x1 and x equals to x2, that means delta y which is equals to 0 at x equals to x1 and x equals to x2. Therefore, the second term of the above expression, this term become 0. Okay, so here this term become 0 means only we have to consider the first term and the last term. So here we will get the integration over, see here, integration over x1 to x2, this dou f by dou y, okay, dou f by dou y minus d by dx of dou f by dou y dash, and this delta y I will take common outside into dx which is equals to 0. Okay, now here therefore, delta y is the only condition imposed on delta y between x1 and x2. Hence, the above equation holds for arbitrary constant, that is delta y, for x lies between x1 to x2. So, here we will get the expression is what? Dou f by dou y minus d by dx of dou f by dou y dash, which is equals to 0, because delta y which is equals to 0. So, for x is lies between x1 to x2. This expression, this equation, okay, so this equation, what we have getting no? So in this equation, we call it as Euler's equation, okay, and here they have given some alternative forms of Euler's equation. So first one is dou f by dou y minus dou square f divided by dou x dou y dash minus dou square f divided by dou y dash into y dash minus dou square f divided by dou y dash the square into y double dash, which is equals to 0. And one more alternate form they have given, d by dx of f minus y dash into dou f by dou y dash, which is equals to dou f by dou x. I hope you understand the today's session, that is what do you mean by variational problem and what do you mean by Euler's equation. Okay, so in next class